Next big thing we are going to learn here, that is called gradient descent. Okay, so by this time we have learned how to quantify our errors of our predictions. We have learned to calculate different activation values starting from kind of first hidden layer till output layers. Now what we have to do, we have to adjust our errors. We have to adjust our weights and biases to take our errors to the lowest possible values. Okay, so pretty much this is kind of the net input, and suppose this is A equal to Z. Okay, so assume this is one dimensional example we are dealing with, and we have only one input value, that is X, so corresponding weight is W, and one bias which was created, and that is B. Okay, and this is the and we are using some of the cost functions. Okay, and this is the pictures, this is the diagram of the parameters and the corresponding cost values, and our target is to reach to the lowest possible cost here. So in this particular case we have to reach this point, okay, or the closest possible to this point. Okay, this is the cost and parameter representations. Now, as we already discussed, initially during our first training we'll randomly initiate the value of W and B. Okay, now assume that we have, with the first initiated random values, we are here somewhere like in this particular point. So we have, this is the cost value, and we have W and B values in this particular case. Once we have calculated the final predicted outcomes, we will get the cross entropy of quadratic cost and corresponding errors. We'll take the derivatives of that error, then we'll jump one very small step toward the lowest cost point. Okay, in the direction of like, okay, in this direction we'll jump little bit. Suppose we'll do the adjustment and we'll reach to this point next. Alright, so we'll do the same predictions. We'll get okay, this point means we'll reduce the value of W and B a little bit, okay, using that the derivative of the cost functions or errors. Once we have the new values of W and B, we are going to do the same calculations to get the cost values or errors once again. On the basis of that, we will again step toward global minimum, and with a small, very little step every time. Okay, finally toward the global minimum, finally we will reach out to this point. This whole concept of reducing the weights or adjusting the weights and biases to get the global minimum of the cost function is known as gradient descent. Okay, sometimes they use different term like global as gradient ascent. Don't get scared of it, like it is negative of the cost function, so the curve negative of the cost function to take the positive of this cost value, like in that case the curve would be different, to find out the global maximum of it. Okay, so let's focus on the gradient descent for now. Okay, later when you will have complete understanding, then you can kind of reverse the concept, or you can understand the term like global gradient descent. The key takeaway here is that with these random initializations, we'll have some of the cost values or values from the cost or error values, and then on the derivative of the cost functions, gradually will step toward global minimum. Our target is to reach to the point where we have the lowest possible error rates. It may not be zero, lowest, or it may be zero some cases, but to reach to the lowest possible cost values. Okay, and every steps we are going to adjust the weights and biases of each and every neurons. And this is very simplified example. Here we have only one parameter. In real life, you will be training kind of millions parameters. So in that case, it is a bit difficult to kind of in that higher dimensional space to draw it. But this is the core concept of gradient descent. Alright, another point which I want to add here, and something called global minimum and local minima. Okay. Often later you will come across some situations where your training process is stuck somewhere, but that is not the optimum solution for it. Okay. For example, we have something like that. Okay. This is the cost diagram and parameters. Sometime during training process, here and there, will end up in this point rather than reaching to this point. These sort of points, which are not actually global minimum, these are called local minimum. Okay, so we have different mechanisms to adjust to prevent our model to end up in this sort of local minimum. Okay, so by this time I think you are pretty clear about what gradient descent is. Okay. Now, alright, so next point we are going to discuss is backward propagation. I think I have given you a quick introduction to backward propagation, how it works. Through the neural network, we'll go from input till the final output. In the final output itself, we are going to calculate the cost or errors. We'll take the derivative of the error function, whatever we are using. We'll step backward gradually. We'll adjust the weights and biases, okay, and we'll reach toward the first hidden layer weights, or all the weights. Basically, we'll adjust the weights and biases. Our target is to adjust the weights and biases in such a way so that after all these iterations, we'll end up in this global minimum. Okay, these feed-forward network, the adjustment of the weights toward backward from the output, this concept is called backward propagations. Okay, this is nothing new. I already have explained, but the concept of using the cost function values or errors every time you are adjusting the weights and biases for each and every neuron in a very small amount to reach to the global minimum. This concept is called backward propagation. Okay. Next critical point is called learning rate. Alright. So the important concept here. So if you see, this is our first entry point with the random initiated weights and biases. Alright. And on the basis of the cost values, we are jumping from this point to this point. Now the point is how much we will jump. That is something called learning rate. Okay, how much you want to learn in a single iterations. Whether you want to go from this point to this point next, this point next, this point next, in this way, or you want to go from here to here next, then here next. Okay, the amount of reduction or these jumping sort of things is called learning rate. This is a very, very critical component from training point of view, we have to smartly take the values for learning rate. If we take too small values, the adjustment of the backward propagations or weight adjustment will be very slow. Your model will be trained very slowly. It will converge very late or after many iterations. Or if you take too high values, your model will not be optimized, or it will not be able to reach to this global minimum. If you take very high learning rate, so from this point it will reach to this point, from here it will reach this point, okay, from here again it will reach this point, because you are adjusting your weights and biases too much, like from here to it will reach here, from here, then here, and these sort of things will happen. So to prevent that thing, this is another kind of hyperparameter which you have to tune it properly to get the best trade-off between the learning, between this gradient descent and number of iterations you need to spend to reach to the global minimum. Another key concept related to the learning rate is called second order learning rate. Okay. In the deep learning concept, we have few new basically logics or functions or algorithms they have, which are called second order learning. So how it works, it adjusts the learning rate automatically depending on the kind of momentum it has. Okay, what I mean to say, like if we see these from, suppose we have one fixed learning rate of 0.01. Okay, now it has seen that it has decreased the cost values from this point to this point. It's pretty much. So by the time when it will reach here, okay, if we do the same sort of adjustment, it will see the cost value is not improving that much. It's not basically not being optimized that much. So what it will do the adjustment of the weights automatically. It will take another fraction of it, maybe 0.1 now, the latest cost constant, depending on the momentum it is, how sliding it is from the higher cost values to the lowest cost values. And it will do very small adjustment here, next very small adjustment here, till it is reaching to this point. Okay, so there are different kind of learning and optimization mechanisms are there. Okay, one of them is called kind of ADAM. Okay, ADAM. Let me write down that thing. Okay, these are kind of optimizers in deep learning terms. Those are called optimizers. Okay, RMS Prof, Adams, and Adagrad. These are different kind of optimizers we have. And out of them, like this, Adam is capable of having second order learning rate. And if you are using like RMS Proc and kind of other sort of adjustment, other sort of optimizer, you may have to manually specify the learning rate you want to implement during gradient descent. Okay, and you have to choose the learning rate smartly. Normally, those are kind of fraction by 10 or something like that, 0.1, 0.01 or 0.001, these sort of things. Alright, so next concept we will have is okay, so there's some concept of how many records you are going to send during training process. Okay, so what happens throughout this network, suppose you have 5,000 training records. 5,000 is very less. Sometimes you have to deal with 5 millions and many more training records. If you send one record at a time to the neural network and tell the network to adjust the weights and biases accordingly, the process would not be that much good, because each and every sample it is getting, and it will do the adjustment very kind of it will do the very fluctuating adjustment to weights and biases. But in the meantime, you cannot send all the examples, like all 5 million records together to the model to train it. Okay, in that case it is going to take infinite or sometime months to train your whole model, and it is cost and very processing expensive process. Okay, so to handle that sort of scenarios, the concept called mini batch was introduced. What happens here? You are going to send the input records in a batch, like sometime those are 64, sometime 124, sometime 256 or 512 or similar sort of things. Normally we use kind of power of 2 to select the number of inputs we are going to send for the network training process. So rather than sending individual training record or all training records together, we will pick up randomly a particular number of samples from the training set and will send them through the network to train the weights and biases, and we'll iterate the process many times, the number of epochs we are selecting here. Those batches are called mini batch. Okay. So it is often recommended to kind of use little higher number of mini batch rather than 10, 15. If you use kind of 120 or maybe sometimes thousands, that would be very helpful, because the network training would be a little bit of generic in that particular case, unless if you plot the errors and number of epochs, you will see like there is a big fluctuate among the kind of errors and the number of epochs in that case. So if you can make it like 512, if you are permitted to use that many number of training data with your current infrastructure, that is very good. Okay, so this is basically the number of samples, training samples you are going to send during the training process. Okay, there is something called epochs. Okay, along with that, okay, this is nothing but the number of times you are going to train your model through the all samples available. Okay, 1000 records, sample training records, and you are doing a epoch of 10. Okay, and you are selecting a batch size of 100. So in a single epoch, the model will be trained 10 times, and the whole data sample will be used for again 10 times. Okay, so basically your model will be trained 10 into 10 equal to 100 times. Okay, this is number of epoch, means how many round of training you are going to do on the complete data set. Alright, so along with that, we during our training process will have something to see it at our side, like what is the training accuracy, what is the validation accuracy. Okay, some sort of concept called metrics. Normally those are kind of mean square errors and whatever things you are selecting, those sort of things will come into picture during our model compilations or during our model fit process. Alright, so these are kind of brief details about the critical component, and during our discussions, whatever new terms I am going to come across, I will come back and I will train them, explain about those new terms. Okay, and we will just add those components in our kind of repository. Alright.